Welcome back to Honors Calculus. In this video, we're going to be looking at some properties of definite integrals. I guess the first thing we need to look at is I just threw an extra word in. Previously, we've just called these things integrals, and now we're giving them a qualifier. It turns out that there are two very different in appearance operations that are fundamentally linked together to the point that it's worth calling both of them integrals. The tool that we have looked at so far has been the definite integral, and we'll see how we can build from that and create something called the indefinite integral a little bit later on in the course. For now, we're going to stick with the definite integral that we already know, and we're going to start off with some nice tools for calculating definite integrals. So let me get my head out of the way and let's do just that. A definite integral is talking about an area pinned underneath a curve in the xy plane. And so we should be able to evaluate a definite integral by looking at it geometrically. For example, if I want to evaluate the integral from 2 to 8 of 2x minus 4 dx, I can try graphing the function that I'm integrating, 2x minus 4, and the limits of integration, x equals 2 and x equals 8. If I can remember which button it is, there we go. I can jump over to Desmos and graph that pretty quickly. And so if we fill in bounded by the function, bounded by the left and right endpoints on x, and bounded by the x-axis, we get this nice triangular region that we're trying to calculate the area on. And I can figure out, based on the points of intersection here, or more specifically, f of 2 and f of 8, the dimensions of this triangle. It happens to be a triangle which measures 6 units on the bottom and 12 units on the right-hand side. With that, I can calculate the integral graphically. Right? Just redrawing that triangle. I don't care about all of the details. What I care about is that that is 6 units in size. That is 12 units in size. There is a right angle here. Area is 1/2 times the base times the height, which comes out at 36. So the integral here is in fact 36. We have the exact value of this definite integral. We don't even have to touch the Riemann sums that we used previously. Let's take a look at one more like that, just to make sure that this makes some sense. And also because I'm not sure if you have seen a function in the form f of x equals the square root of 25 minus x squared. If we go ahead and graph this curve, we get a shape that looks like this, which is a bit of an odd looking arc, which you may recognize right away, you may not. If you don't recognize it right away, let me come back to my notepad and rewrite the graph here is y equals the square root of 25 minus x squared. And if I square both sides of this equation, I get y squared equals 25 minus x squared. And if I add x squared to both sides of this equation, I get x squared plus y squared is equal to 25. That is an equation that you should recognize. It's the equation for a circle of radius 5. And so my graph, I'm not getting the entire circle, I'm just getting part of it. I have here half of a circle. So the area of this curve, or the area under this curve, the value of this integral is going to be 1/2 of the circle of radius 5. And that's exactly how I'm going to go about solving it. Right, so 1/2 the circle, r equals 5. Area of a circle is given as pi times r squared. R in this case is 5. 5 squared is 25. So I'll call this 25 pi over 2. If you grab out a calculator and punch that in, 25 times pi divided by 2, my calculator tells me is 39.27-ish. But 25 pi over 2 is good enough for our purposes. All right. So when we have a nice curve that is well behaved and that happens to give us something we know how to deal with, we can jump in very quickly and calculate the area. I would like to build that process up just a little bit. And so the next thing I want to do is look at a couple of theorems. If our function f is continuous on the interval from a to b, then the integral from a to b of f of x dx is defined. And that's a bit of a mouthful. So instead of saying the integral is defined, we often will say f is integrable on AB. I think that this theorem is kind of obvious. If you have a function that is continuous, then you have a function that you can calculate areas, right? A continuous curve lets you draw the line underneath it, lets you define an area, give you something to work on. One of the things that's interesting about this theorem is that it does not say that if f is not continuous, then f is not integrable. And in fact, most of what I want to build up to today is being able to evaluate the integral of a function which is not continuous. But we'll get there a little bit later. All right, so if the function is continuous, then the integral is defined. If the integral is defined, that does not necessarily mean that the function is continuous. Um, and because of that kind of one-directionalness, this isn't really a proof, but just what I said before. If the function is continuous, then the area under the curve is a well-defined region. You should be able to use a continuous curve as the top, draw straight lines on the bottom and on the sides, and get area of a well-defined region. So not quite a proof, but a good idea on how to get there. Next theorem I will be proving claims that the integral is a linear operator. Remember that linear means that if I have the integral from a to b of some combination a times f of x plus b times g of x, I should be able to split it up as a times the integral of f of x plus b times the integral of g of x. And to prove this, I'm going to use the limit definition. The integral from a to b of a times f of x plus b times g of x is the limit as n goes to infinity of the sum k goes from 1 to n of a times f of xk plus b times g of xk times delta x. Right? That's the definition of the limit, or that's the limit definition of the integral. And now we have a summation here, and summations are linear. So I can split this up as a times the sum f of xk times delta x plus b times the sum g of xk delta x. And limits are also linear. So I can split this up as a times the limit on the sum of f of xk delta x plus b times the limit on the sum of g of xk delta x. And yeah, I should have all these limits as n goes to infinity. I should have all these sums as k goes from 1 to n. But I'm lazy and I don't always write all of that in. The important thing is that the limit on the sum of that particular formation is in fact exactly what we mean by the integral from a to b of f of x dx, and exactly what we mean by the integral from a to b of g of x dx. And so if you have a couple of things being added together, you can break them into pieces like this. I've got one other tool that is very important for splitting up integrals, and I want to be able to use both of them together before I get to my next example. The other tool is something that you're very familiar with when it comes to working with area. If you have a complicated region that you are trying to calculate the area, you can break that region up into parts. You can calculate the area of each part, and you can bring everything together. When I write that out in terms of integrals, it looks a little bit goofy, but that's exactly what I'm going to be doing here. So the claim here is that let f be integrable on AB, and let C be something inside of AB, then the integral from A to B of f of x dx is in fact the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Hidden inside this, integral from A to C and from C to B are both defined. So we get that on any piece of the integral, or of the interval on which the integral is defined, the integral is still defined. I could try to set this proof up a little bit more elegantly. I'm calling this proof in quotation marks because I think the picture gives it a lot more sense than anything that I could try to do by hand. But if I get my function here, I draw in my A and my B, and I pick my other point in the middle here called C. Notice that what I'm doing is I'm calculating the area of this region, and I'm calculating the area of that region, and I'm adding them together to get the entire thing. The area of the entire region is the sum of the areas of each piece. Right. Not exactly a mathematical proof, but I think it gets the point across, and I think that that visual is more important at our current level than anything else we might want to do. But with all of that together, I can get a piecewise defined function here. F of x has two pieces. 1 plus the square root of 9 minus x squared if x is between -3 and 0. And my second piece is going to be 12 minus 2x all over 3 if 0 is less than x. And I want to evaluate the integral from -3 to 3 of f of x dx. The first thing that I'm going to do is treat this very similarly to how I've treated things in the past. Go into Desmos and graph it. And you can see here that I'm going to have an area that is going to be well defined, but it's really broken into a bunch of pieces. Over here, I've got the, well, half of a semicircle, a quarter circle, I guess, but it doesn't come all the way down to the x-axis. It stops a little bit higher. Over here, I've got this wedge-shaped piece, which is going to be a triangle, but again, it doesn't come all the way down to the x-axis. It stops a little bit higher. And so that's one of the first things that I want to do. If I can draw a horizontal line right here at y equals 1, then I've got a circle and a rectangle below it. Over here, if I can draw this line, figure out where that point is, plug in x equals 3 in the second piece. 12 minus 6 all over 3 is 2. So this line is y equals 2, and I've got a triangle above that. And so that's how I'm going to calculate the area of this thing. Get my head back out of the way, go back to my notepad, and I'm going to draw this shape as carefully as I can. And I'm going to divide the shape up into those 4 pieces. I've got, let's use a thicker line. I've got a quarter of a circle. I've got a triangle. I've got a rectangle. And I've got another rectangle. All right, so 1/4 of the area of a circle, pi times 3 squared. The area of a triangle, 1/2 times the length of the base, which is 3, times the height, which is 2. I've got the rectangle over here, which is 1/3. I've got the rectangle over here, which is 2/3. All right, so I can break the shape up into all these pieces, and that's all that those 2 theorems are really telling me that I can do. And so if I do just that, let's see, I'll have 9/4 pi, I'll have 3, I'll have 3, and I'll have 6. So I guess all told, that is 12 plus 9 pi over 4. Again, you can get a decimal approximation if you would like, but I'm happy to leave it as that. All right. There's one last example that I want to look at here today, talking about area. So far, all of the functions that we have considered have had the function appearing entirely above the x-axis. We haven't looked at anything where the function drops below the x-axis. And so I want to do that before we run out today. So let's just go ahead. I'm going to create a fairly basic piecewise step function. I put the or equals on the wrong side of that. Sorry about that. Let's consider this piecewise function with 3 pieces. F of x is -1 if 0 less than x less than or equal to 1. F of x is 0 if 1 less than x less than or equal to 2. And f of x is 1 if 2 less than x less than or equal to 3. This is a very simple function. I'm confident in my ability to draw it by hand. I don't need to go to Desmos or anything like that. But we're going to have a piece here. We're going to have a piece here. We're going to have a piece here. Right? Well defined on that side, undefined on this side. And so if I start to draw in my regions here, I've got this part down here. I've got that part up there. And I think that it is obvious that if I choose a Riemann sum with n equals 3, I'm not going to get anything better than that. Right? I guess I should have actually written down, sorry, I got ahead of myself. I'm looking for the integral from 0 to 3 of f of x dx, right? The entire place where this thing is defined. All right, but picking n equals 3, I get my delta x is 1. I can figure out what x naught, x1, x2, and x3 are. I can go to my Riemann sum, and I can get that the area here is going to be, right, the sum k goes from 1 to 3 of f of xk times delta x. And when I plug in x1, x equals 1, I get out -1. When I plug in x2, x equals 2, I get out 0. And when I plug in x3, x equals +1, I get out +1. So -1 plus 0 plus 1 is 0. Clearly, looking at this figure, there is area underneath that curve. But it's not really all underneath the curve. Over here, where the curve itself is below the x-axis, the area that we pinned is above the curve. And area above the curve, we're going to treat as negative area. That's what the formula tells us we're supposed to do. This is one of those things in mathematics that is kind of goofy. It doesn't feel like it makes sense. And in fact, mathematicians, as they were developing this, said, no, this doesn't make any sense. We can't do this. And so there were two branches of mathematicians. There were mathematicians who just said, okay, this idea of the definite integral only applies when the function is positive. If the function is negative, it's nonsense. The other group said, well, sure, it's nonsense, but let's do it anyway. The shocking thing is that that group found that this application, calling the area negative, actually correctly solves a number of problems in physics and engineering. It's goofy. Negative area makes no sense. But if we pretend that it makes sense and we continue to use it anyway, it solves problems for us. That's mathematics in a nutshell. We come up with something that makes no sense. We try to use it anyway. We find out that it is incredibly valuable. There is no such thing as pure math without an application, because every time a mathematician comes up with something that says, there are never going to be any ways we can apply this, it's not long before an application comes around and says, that's exactly the thing I've been searching for. Right. We don't have enough time, unfortunately, to get into any of those applications, but let's look at one last example where this negative area actually does show up. Get my head back out of the way. I'm again going to go with a relatively simple example so the graph is easy to draw. Let's take a look at the integral, maybe not in red. Let's take a look at the integral from 0 to 5 of x minus 3 dx. All right, the graph y equals x minus 3 is very simple to draw. It is, in fact, the line of slope 1. And when we pin in our limits of integration, we get these two regions. We have a negative triangle, and we have a positive triangle. All right, so the area of the negative triangle is going to be negative, and then 1/2 times the base, which is 3, times the height, which is 3. The positive triangle is going to be plus 1/2 the base, which is 2, the height, which is 2. All right, so we get -9/2 plus 2, all told is -5/2. All right, the area of this figure comes out as a negative value. Does a negative value make sense? Not really, but again, applications exist where it does, right? Calling this area is being very loose with the word area, but saying that the integral comes out at a negative value is still perfectly fine. All right, let's wrap up with one more problem like this for you to take a look at. I would like you to calculate the integral. X goes from 0 to 4 of 2 minus 2x dx. All right, take a couple of minutes, see what you can come up with there, and I'll see you in the next video.